All right, welcome everybody. Good morning, good afternoon, good evening, wherever you are. Welcome to the Staties August webinar. Today, my name is Martin Bezener, and I'm a statistician here at Staties Incorporated in Minneapolis, Minnesota in the United States. Today I'll be talking about automated model selection for response surface modeling. Just a brief note here. There are quite a few attendees with us today, so to avoid any disruptions, everybody is muted. So if you speak into your microphone, I will not hear you. If you do have any questions during the webinar, there is a little questions feature on the GoToWebinar interface, so feel free to submit any questions in that location. I'm joined today by my colleague Wayne Adams, who is also a statistician here at Staties Incorporated, and he will be answering those questions as they come along. If you have any questions, after the webinar, feel free to email us at stathelp@staties.com, and we'll try to get to those. We'll try to answer those as soon as we can. Finally, the presentation will be posted at this location right here at staties.com/webinar. It will also be given again tomorrow, and it will also be posted on our YouTube channel. So this presentation is targeted towards practitioners, so there's no theory that we need to worry about, and we'll try to keep it to around 45 minutes. So having said that, why don't we go ahead and get right into it. So just a brief word about Staties Incorporated. We are, for those of you that are new, we are a provider of design of experiments software, namely Design Expert, and we also do some training and consulting. We've been around for approximately 34 years now, since 1982, and we're headquartered in Minneapolis near the University of Minnesota. We employ over a dozen people in our office here in Minneapolis, plus we have a wide-spanning worldwide network of resellers. Our mission has always been statistics made easy, so keeping things simple. And we've received numerous awards and honors over the years from the ASQ and from other organizations. What are we going to talk about today? Well, again, the main topic is automatic model selection. We'll start by talking about the design of experiments process, just to kind of lay out some of the groundwork. I'll do a quick example of how most people do model selection and show why that may start to become difficult in certain situations. Then I'll talk about the actual background behind model selection, focusing on why and specifically how, including automatic model selection. I'll do two examples that are a little bit more complicated in the Design Expert software at the very end, and then we'll conclude with some hints, practical tips, and tricks that you can use when you're on your own. So let's start with the DOE process. So ideally, the DOE process should look something like this. You should always start, or typically you start with some sort of objective or goal. For example, you'd like to increase the yield of a chemical reaction by 2%. You'd like to maintain the quality characteristics of a product, but perhaps produce it at a cost that's less than what you're producing it at currently. In order to achieve this goal, you need to change something about the process. the things that you can change are what we call factors. So you need to determine what is it actually that you can vary to try to achieve this objective or goal. Once you have your factors of interest, in some cases, in some experiments, there may be a range finding step where you find the safe, low, and high values of each factor that you can actually run. If you have lots and lots of factors in your first step, you may also do a screening experiment to try to reduce the number of those factors to a more manageable subset. Once you have kind of your final list of factors of interest, a full characterization experiment follows. Afterwards, when you collect the data, you need to build a model. You need to check your model, and then you can interpret, optimize, and if possible, confirm the results from the optimization. Today, we're going to be talking about exactly one of these steps here. Select model. That'll be the focus of this webinar. So we have assumed, in this webinar, we have assumed that you already have your data. There are plenty of presentations that we've given and resources available for all of these other steps here. But we'll just focus on actually selecting a model, and in particular letting the computer select the model for us. Let's just look at a simple example of model selection. You've probably done model selection. So let's say we have a central composite design. This is essentially a two-factor response surface design that has temperature as a factor and time as a factor, with the response being the hardness of whatever it is that we're putting in the oven. So again, we have two numeric factors that we think may affect the hardness as we vary the numeric factors. Let's suppose we fit a full quadratic model which contains the intercept, which contains the linear effects of time and temperature, the two-factor interaction of time and temperature, and the quadratic effects of time and temperature. So there are a total of 5 non-intercept terms, in particular these terms here, in the model. Now, even though we put them in the model, that doesn't necessarily mean that all of these are important. So let's go ahead and actually fit the full model. Well, here's what we get in Design Expert. Notice that up to this point, you may have done something like this. You may have checked these p-values, identified if any of them are large, and concluded that if the p-value is large, then that term is not important. In other words, its effect on the response is probably 0 or very close to 0. In this case, we note that a squared, the quadratic effect of a, its p-value is quite large. Okay, it's greater than some threshold. Typically, that threshold is 0.05. So there is little evidence of a affecting the response in a quadratic manner. What you may have done in the past is you may have simply removed this term here and refit the model. That's easy enough. And congratulations, we just did a model selection here. We ended up with this model here, which includes the linear effects of temperature and time, the two-factor interaction between temperature and time, and the quadratic effect of time here. So notice that all of these terms now look significant. Okay, so that seemed easy enough. Notice that by taking out a squared, I didn't put this information on the previous slide, but if you actually go through this on your own, you'll notice that the lack of fit p-value goes up from 0.4 to about 0.46. The adjusted R-squared goes up by a very tiny fraction, and the predicted R-squared goes up as well. So the question is by taking out a squared, which is an irrelevant term, is it a coincidence that we see these improvements in the model? So we did our first model selection of the webinar. what we did is we fit the full model and we took out any terms that have a p-value greater than 0.05. Easy enough. Let's suppose we had a slightly more complicated example here. So suppose we had a combined mixture process design where we were trying to optimize coffee flavor. Let's say 3 of our factors formed a mixture, so these are the components of a 3-component mixture. The amount of light beans, medium beans, and dark beans that we're putting in. And let's say that we have a process factor, which is the amount of coffee, and the grind size, which is a categorical factor. Suppose that we're interested in starting with a quadratic by quadratic model when we cross all of these terms with one another. This full model would have a total of 41 potential terms in it that we would have to deal with. This isn't actually an experiment that we did in our office. Originally, we were going to use a 5-component mixture, which in this case, the full model would have contained around 105 terms. Now, it's not easy in this case to select a model manually, having to deal with 105 terms that you're pulling in, you're taking out, and so on. And we've seen cases where this has gotten even more difficult. So we talked a little bit about kind of the intuition behind model selection, but let's talk about it a little bit more. So the why and the how. The ultimate goal in response surface, and when I say response surface, I also am including in that mixture experiments, because the goal of those is also usually to fit a predictive surface. So the ultimate goal in RSM is to build a model that adequately describes the effect that the factors have on the response. So when we vary our factors, how does the response change? And they may not just be the linear main effects. There could be interactions, there could be quadratic cubic effects, and so on. Then what we do is we use that model for optimization. Maybe we want to find an operating window. Maybe we want to find the maximum, the minimum, and so on. Remember, you're probably not going to get the model exactly correct. There is a famous quote that says, all models are wrong. Some of them are useful. So really, when we're building a model in response surface methodology in RSMs, we're building an approximation. And hopefully that approximation is good enough that the optimization results are decent. Now, of course, there may be factors that you varied in the experiment that don't actually affect the response in a meaningful way. In other cases, the factors may affect the response, but only linearly. In other words, their higher order effects like quadratic or cubic may not actually be present. So our goal here is to build a model that contains all the important terms. And you may be thinking to yourself, well, why don't I just put everything in the model to be safe? Okay, well, we'll see why that's not a good idea. So let's just look at a couple really simple models here. Very intuitive example. Suppose we wanted to predict a person's weight, but we cannot actually put them on a scale. And we want to build a predictive model. So I input some information and I get a weight prediction. Let's say that I create a model that predicts somebody's weight as a function of their age. Okay. This model is probably not completely useless, but if I tell you this guy is 42 years old, tell me what his weight is, predict his weight, there's probably going to be a lot of error in those predictions. So this is a model that's too small. Let's say we go up a little bit to the next level. We say, okay, we'll predict somebody's weight as a function of their age, their height, and their daily calorie intake. Well, this model is fairly small. There's only 3 main effects here, and it's probably reasonable intuitively. I mean, I'm not a nutritionist or a physician, but this to me seems intuitively reasonable. It seems like all of these would probably affect somebody's weight, and it seems like these 3 factors here are, somewhat independent of one another. We're not starting to put in redundant factors. We could go up another step here to this model and say we'll try to predict somebody's weight as a function of their age, height, their daily calories, how much exercise they do each day, and their waist size. Okay, now this model is larger, but to me it seems like it could still be reasonable. However, I would start to worry about some of these factors being redundant, meaning if I know somebody's age, height, daily calories, and daily exercise, I could probably get a good prediction of their waist size as well, but intuitively this doesn't seem like a terrible model. Here's a model that to me, if somebody might be absolutely worried and say, well, I don't know what's important, so I'll just put in everything. So I'll put in their age, their height, their calories, the daily exercise, their waist size, their eye color, shoe size, hair color, car color, their retirement account balance, the first digit of their zip code, whether or not they wear glasses, whether or not they like rap music, and so on. This is a model which intuitively I would consider excessively large and probably not reasonable. So in an intuitive level, I would probably say I want to either be somewhere around here or somewhere around here. If you have two reasonable models, one of which is small and the other of which is large, so for example here we had two reasonable models, the second one and the third one of which is small and the other of which is large, the smaller model does offer several advantages. Well, A, it's simpler. This isn't rocket science here. It's easier to work with. It's also easier to interpret simply because there's fewer things to look at. There's fewer interactions going on. There's fewer higher order terms. So what you should get is a clearer understanding of how each factor, how each term that you put in the model actually affects the response. Now, large models are not always bad, so I don't want to say that large models are necessarily bad, but a model that's excessively large, okay, note the word excessively large, is going to encounter problems. First of all, you're probably going to have issues with redundancy, where you start putting in terms that are related to one another. What's going to happen is that those terms are going to compete with one another in the model to explain the same feature in your data set. And this is going to cause poorly estimated model coefficients. You may end up with issues with collinearity. Your prediction quality and accuracy and precision will likely suffer. And you also will likely encounter an issue with irreproducible results. So this is probably the biggest one that I've seen people run into. What happens is they overfit their model to the particular data set. Then in the future, they're not able to reproduce those results because they ended up fitting the noise that was encountered in the experiment. Well, of course, the noise from experiment to experiment or the noise from experiment to production may not be consistent. So you don't want to be fitting noise. You want a model that's general. Fit the trend, don't fit the noise. As we saw earlier in that coffee illustration, there may be too many terms to deal with, so it may be hard to select the terms manually. You also may encounter a situation where there are more model terms that you're considering putting in the model than you have runs in the experiment. In a situation like this, you cannot fit the full model and simply drop the terms. You need to fit a subset. And if you have 105 terms and you can only fit 60 of them at a time, that's a lot of subsets that you're going to have to be considering. So computers are fast. Why don't we let the computer pick a model for us? Now notice how I emphasized A. I didn't say pick the model for us. So the idea would be, well, tell the computer, fit a bunch of different models, and then simply pick the best one. So let's find out how this actually works. In every automatic model selection problem, you're going to need to specify a candidate set. What this candidate set is, it's a list of the terms, the model terms, that you want the program or the algorithm to consider. It won't consider anything outside of those terms. So let's say we had a two-factor experiment and we have 4 terms in our candidate set. We have the linear effects of A and B, their interaction, and the quadratic effect of B squared. Perhaps we know ahead of time that we don't really care about A squared. You have to pick the candidate set. One thing you can do is you can do a forward selection. So if you've ever heard the phrases forward selection, backward selection, stepwise, BIC, p-value selection, and kind of wondered what they meant, we're going to talk about it right here. So how would the computer do? So forward selection is one option that you can tell the computer to use. How does forward selection work? Well, what we need is we need a base model. In other words, start with a model that the computer is going to start on and then build off of. So and what the program will do is it'll start with the base model and then just add terms to the model one at a time until there are no more good terms left to add. Now notice how the word best is in quotes here. There's a reason for that. I'll define what best means, what good means, what bad means in just a few more slides. So for now, just think of it as at an intuitive level. What the forward selection will do is it will fit the following 4 models. It will fit, so in this case, the base model will be just the intercept. Okay, notice how all these models contain the intercept. So what the program will do is it'll add A to the base model. Then it'll take A out and put B in. Then it'll take out B and put the two-factor interaction in. Then it'll take it out and put B squared in. And what it'll do is it'll pick the term of these 4 that produces the best improvement, if there is an improvement, and actually add it to the model. So let's suppose in this case B is the best term. So then what the forward selection will do is it'll fit the model with the intercept plus B, and then add A, take out A, add AB, take out AB, add B squared, take out B squared. It'll consider the remaining terms in the candidate set one at a time. The term that produces the best improvement of these 3 will be added to the model. And this process will continue until adding additional terms doesn't make the model any better. So here's an example sequence. Start with the intercept, B gets added, B plus A gets added. So forward selection is a build up, one at a time build up procedure. We could also tell the program, basically any statistical software, to do a backward selection. Once again, just like in the forward selection, we need a candidate set. This is all of the terms that we want the program to consider. It's not going to go outside of this list. So what the backward selection is going to do is it will start by fitting the full model. And by full model, I mean it'll fit everything in this candidate set here. Then what it's going to do is it's going to look at this full model and find out what is the worst term. In other words, when I drop the term, when I drop these terms, which one will produce the biggest improvement in the model? And it'll keep going until only good terms are left. So just an illustration here, we would fit the full model, and then what the program would do is it would go ahead and fit these models here, basically dropping each of these terms one at a time. The program, what it'll do is it'll pick the term that produces the best improvement when dropped, if any, and then choose it and actually remove it from the model. So suppose in this case B squared is the worst term in the model. So the model becomes now the intercept plus A plus B plus the interaction between the 2. The program will do is then it will start with this model here that I'm just going to circle so you can see it. And it'll go ahead and once again start dropping terms one at a time. and it will pick the term that produces the best improvement when omitted. If anything is chosen, it will produce the term that gives the best improvement when omitted, okay, and choose it and then drop it from the model. And it will keep going until the model cannot be improved by dropping further terms. So here's an example sequence. Here's the full model. Maybe at the first step, the program will drop B to give this model. Then maybe it'll drop AB to give this model. And then maybe it'll drop B squared at the very end to give this model. So you want to think of backward selection as kind of a one-at-a-time pruning procedure where it'll reduce the model one at a time, one term at a time. Finally, probably the third most common selection method that most software implements is what's called all subset selection. So once again, we need this candidate set. What all subset selection will do is it'll fit every possible model that it can create from this candidate set and pick the best one. So in this case, there are a total, I'm not going to go through all of these, but there are a total of 16 models you can create, ranging from the intercept-only model all the way up to the full model. And this is a good procedure. This is a very good procedure. However, this can be very time-consuming if you have a lot of terms in the candidate set or if you have a very large data set, because it needs to basically go through every single model and fit it and look at it. So it's a very brute force, greedy procedure. Now, I said computers are fast, but the problem is computers are also fairly dumb. In other words, they cannot do anything that you don't tell them to do. So the program, and by program I mean any software, cannot intuitively eyeball a good model. Notice how I've used the words good model up to this point. I've used good model term, the worst model term, and so on. The program cannot just look and give an opinion. It needs a numeric score to compare models. So in order to tell whether a model is one model is better than the other, it needs to compute some score and pick the model with the better score. Now there are many model scoring methods that are available. Most of them have the following form. The score is some sort of blend of the goodness of fit. So this is our goodness of fit is good. That'll help the score. However, there's also a model size penalty. So most of these methods, or a lot of these methods, will blend together the goodness of fit of a model along with the model size penalty. Why penalize the model size? Well, when you add model terms, even if they're complete noise, it'll still look like it's improving the goodness of fit, even if you're adding something that was completely unrelated to the response. For those of you that are familiar with analysis of variance, if you keep adding factors, you keep adding terms, the residual sum of squares can only go down. Okay, however, some terms may not improve the goodness of fit enough, right? So here's the word enough to be worth including in the model. And remember, a few slides ago I talked about what happens if a model is excessively large. You're going to get issues with redundant terms, collinearity, reproducibility of results, and you're going to have a hard time interpreting what's going on. So the computer, what the program needs to do is it needs to score each model and then simply pick the one with the best score. Now, we need to come up with a score, or do we? Well, actually, it turns out we don't. So if this slide is looks a little bit challenging, I'm just going to let you know that this is probably the most technical slide for the remainder of the presentation. So this is about as tough as it gets here. So we don't actually need to come up with a score because there are many well-established model scoring methods that have been developed over the last 30, 40 years. Three very popular model scoring methods that the program can use when it does automatic model selection include BIC, which stands for the Bayesian Information Criterion, AIC, Akaike Information Criterion, AICC, which is the corrected Akaike Information Criterion for small samples. Note that all three of these methods blend together, have a component that's a goodness of fit component and a size penalty. A goodness of fit component and a size penalty. AICC is simply a function of AIC plus a small correction for small samples. So essentially it's similar to AIC, and if you have more and more data, then the AICC and the AIC will converge to one another. So the BIC is a function of the goodness of fit, which is this -2 times log likelihood. You don't have to worry about that, but it's related to the residual sums of squares in linear regression. So you could think about it that way, plus a model size penalty. So notice that the BIC for every term, notice that P here is the number of terms that you're putting in the model, and N is the number of runs here in your experiment. Okay, sorry, I probably should have defined N here. So the BIC will penalize a model at a rate of log N. So for each term you put in the model, it'll penalize the model at a rate of log N. The AIC will penalize each model at a rate of 2. So for every term you put in the model, it'll penalize the model by 2. I believe if N is greater than 8, the BIC penalty starts to become much more severe. Now you may be wondering, why is one of these log N, why is one of these 2? Well, these numbers have a theoretical basis that was developed that we really don't care about in this webinar, but these weren't chosen arbitrarily. In a perfect world, this log N and this 2 here actually, they were chosen for very specific reasons. So BIC will generally penalize the inclusion of terms at a much more severely than AIC will. And AIC has some, let's say, poor behavior in very small samples, which is why this corrected AIC was developed. Terms also, we'll see that you could also include or exclude terms based on p-values, just like we did at the very first example where we looked at which terms have large p-values and we took them out. For the remainder of this webinar, we'll talk about AICC and BIC. In fact, we'll really only focus on AICC. Caveat here, when using AICC and BIC, lower scores are better. So if you have 2 models that were fit to the same data set, and you want to pick one based on its BIC score, you'd pick the one with the lower BIC. Same thing with AIC, same thing with AICC. Okay, so lower is better. Let's actually just quickly see how Design Expert does this. So we'll go back to the very first example, which was the 2-factor central composite design that had temperature and time as factors. And we'll go ahead and we'll let our candidate set be the full quadratic model. And we'll try a couple of methods just so that you can see how Design Expert does this. Remember, when using AICC and BIC, and again, we'll just really focus on AICC here, lower is better. So I'm going to go ahead and open up Design Expert 10 here. So this is my data set. It's a 13-run experiment. This is what the experimental design looks like. So I have my center points, my factorial points, and I have my axial points here. And what I'm going to do is I'm going to click on the response here. So hopefully everybody can see I'm going to click on the Model tab. Notice that Design Expert will recommend a starting model, which in this case happens to be the full quadratic model. Notice that there's this button here, Auto Select. This is the magic button that'll get you to the automatic selection interface here. What I'm going to do is I'm going to show you how AICC Forward works here. Done. So remember, anything that has a green M by it is in the candidate set. That's how Design Expert works. So anything that has a green M has will be in the candidate set. Now let's say, for example, I wanted to put an A squared B in the candidate set. I would simply double click on this term here, and I could double click to remove it as well. So I'm going to go back to the automatic selection, use AICC Forward, and start. Let's see what the program did. Well, first of all, it added the intercept to the final model. The AICC of the intercept-only model was about 99.1. Then what the program did is it considered putting in each of these terms one at a time and computed the AICC for each of these models. The model with just A in it, with just B in it, with just AB in it, with just A squared, and with just B squared. And it computed the AICC of each of those models. And it picked the one with the lowest AICC, which turned out to be the model with just the B squared model. The AICC of that model was 96. Now what it did is it went through the remaining terms and tried to see if adding any of the remaining terms produces a model whose AICC is lower than 96. Well, turns out we're in luck, because A, when we put in A, it gives an AICC of 89, and so on. So then it goes through again and it puts in AB. Then it goes through again and it puts in B. Finally, it puts in everything but A squared. The model with everything but A squared has an AICC of 66.7. If it does add A squared, the AICC goes up to almost 73. So it would not put in A squared. It cannot put in any of the remaining terms. And if you click accept, you'll notice that A squared is now unhighlighted. And if I go to the ANOVA, I basically get the same results I got when I did the p-value selection. I'm going to go back here. I can do an AICC backward selection. Notice that it will compute the AICC of the full model and then drop terms one at a time. When it drops A squared, now we're going backwards, remember, the AICC goes down. However, after dropping A squared, after it drops the remaining terms one at a time, the AICC only goes up, so it stops dropping terms after it dropped A squared. One little note here, you could also do the p-value selection. Similar, this is basically like what you would do by hand. So what would happen is if I did a p-value selection, the program would simply start with the intercept-only model and then add the terms in one at a time and pick the term that had the lowest p-value. Then it would try the remaining terms one at a time and pick the term with the lowest p-value. And it would keep going until all of the p-values are above whatever threshold you put in. So in this case, the threshold I put in was 0.1. Okay, and I also see here that I have BIC. I have adjusted R squared for this all subset search. We have BIC and so on. So in Design Expert 10, the automatic selection interface was completely redone, and it's a lot more customizable and hopefully easier to use. It's been fairly well received, so we're pretty happy about it. So some advantages to automatic model selection. So that was a simple example. We'll do two more complicated examples of things that you might run into on your own at the very end. So some advantages to automatic model selection. It's easy. It's fast. It's customizable, meaning you can tailor the direction, you can tailor the criteria that you use to your particular problem. And it usually produces a model that's at least somewhat reasonable. Now, it may not necessarily give you the right model or even the best model, okay, but it should hopefully at least give you a reasonable starting point. And notice how, and I also say it doesn't require subject matter knowledge, so if you know absolutely nothing about your process, it's an objective selection method. Now, notice I put a little caveat in here. See the next slide. Some disadvantages to model selection. Well, namely, it doesn't use subject matter knowledge. So like I said, computers are fast, but they're dumb. They can only assess or do what you tell them to do. So even if objectively a model looks good, the computer can't say, well, that doesn't seem right. That's on you. That's on the subject matter expert to do. Different criteria and different methods can produce different models. Now, that didn't happen in the previous example, but we'll see where doing a forward selection and doing a backward selection end up giving you different models. What do you do? And in some cases, the models may be very different. There's no one correct answer in most situations. Also, automatic selection, and we'll see this in just in the next few slides here, especially forward or backward selection can be somewhat problematic when you have a constrained or irregular design space. This also holds true if you have a mixture experiment where you're experimenting over a simplex or some subregion of the simplex. There may be an order dependence, so the order in which the terms are added or dropped may end up producing different models in the end. You may have an issue with correlated terms. Okay. There's also this issue of multiple testing and comparison, meaning the computer or the program tries to put in a lot of terms one at a time. Now there's a chance that it makes a mistake every time it puts in and takes out a term, every time it keeps a model. Do that many, many times, and the probability that there is an error somewhere along the way approaches 1. So you want to be careful, and we'll give you some tips on how you can get around some of this. Okay, so let's actually do 2 more complicated examples here and then start wrapping up. So we already saw automatic model selection on a relatively simple problem where pretty much all methods would give you the same model. We'll now look at 2 more involved examples with Design Expert 10, and we'll see how problems can arise and maybe what you can do. So we will look at a constrained optimal RSM, and we'll look at a highly constrained optimal mixture design. Okay, so the first example here is a 3-factor optimal RSM design. So I've simplified this problem quite a bit so that we don't have to worry too much about the science, since we don't have all that much time. This way, so everybody understands what's going on right away. So Phil, you could pretend these are any factors. A goes between 0 and 0.8, B goes between 0 and 0.8, and C goes between 0 and 2. Now there's an additional constraint that the sum of A and B has to be between 0.5 and 0.8. Turns out that if you put this in Design Expert, you get a design space that looks like this. At any level of C, you get this kind of 4-sided trapezoidal figure here. This isn't a regular design space, but this certainly happens in practice. Now, I'm going to go ahead and actually do this in Design Expert, so hopefully you'll be able to see. And Wayne, maybe if you want to let me know if you can actually see this well, I would appreciate it if you can actually see the text. So here is the design that I was talking about. So this is a 20-run design. I'm going to go ahead and start with the quadratic model, and I'm going to look at the ANOVA. So I always like to actually look at the ANOVA of the full model, if possible, and just to get a sense of what's going on. Looks like here, C is the only significant term. All these other terms have large p-values. So you might be thinking to yourself, well, if you didn't know about automatic selection, you would drop everything and just keep C in. Well, we'll see that that's not really the best method here. So what I'm going to do is I'm going to use, so just for those of you that weren't able to see the text, I'll show you what it looks like, what the full quadratic model looks like on this slide here. So once again, it looks like C is the only term that appears important. So the question is, and notice the question mark here, do we remove everything but C and simply refit? Okay, let's try automatic model selection here. So what I'm going to do is I'm going to go back to this model tab here, and I'm going to go to the automatic selection. I'm going to use AICC forward selection, and I'm going to write down on a paper, on my piece of paper that I have in front of me, what terms were chosen. And I'll go ahead and fit the ANOVA. Now notice that the program will offer to correct hierarchy for you, right? Because it picked AC, but A was not picked. So it'll actually put A back in the model. And this is the model. So I'm going to write this down on my piece of paper. And now I'm going to go back and start with the quadratic model and do an AICC backward selection. Wow. If I go back and I correct for hierarchy, I get a model that's pretty different when I go backwards. Okay, so what's the story here? So you'd think that going forwards or backwards should give you the same model, but it doesn't here. So for those of you that, again, that can't see the text very clearly, we used forward and backward selection here with AICC, considering the full quadratic model. That was our candidate set of terms. The forward selection picked B, C, and the interaction between A and C, and then eventually we added A back in to correct for the hierarchy. The backward selection picked B plus C plus AB plus AC plus B squared, and then added A back in for hierarchy. Now if you go through and you use BIC or p-values, you should get something pretty similar. They may be off by a term or two, but AIC is C is what we're using here. So the question is which model to use? Okay, you have two competing models. This is not a situation that's obviously ideal, but hopefully we can actually pick one of these. So what we can do is we can actually compare the two models. So compare them based on these statistics here. So fit them both and actually examine them. So first thing I would do, if I were consulting with somebody, is I would ask somebody, does one of these models make more sense from a subject matter standpoint? Does it make sense that B squared has this quadratic effect? And so on. So I'd first ask to see if any of these make more sense. What I'm going to do is I'm going to compare the backward model with the forward model. I'm going to see that the lack of fit p-value is higher in the backward model, although the forward model doesn't appear to fit poorly here. I'm going to look at the predicted R-squared since I'm doing predictions in response surface methodology. Notice that my predicted R-squared of the backward model is quite a bit higher than the forward model. And notice that actually the AICC of the backward model is lower. Remember, AICC, lower is better. So notice that the backward selection model looks to be quite a bit better just from these numerical scores. Because the design space is constrained, the order in which terms are added or dropped may cause a big difference in your final model. This happens all the time when you have constraints on your design space, or if you're working with a mixture, or if you have a design that's not balanced. Now notice that the backward model, all of these terms, so A was put in, so I'm going to fit just the backward model. Now you could ignore A here because it was just put in to correct the hierarchy. But notice that when I fit the backward model, look at all of these significant p-values here. When I fit the full model, I had just one significant term. So if I were to fit the full quadratic model, drop everything whose p-value was large, I would end up with just C. But when I do an automatic selection and kind of consider adding terms in one at a time or deleting terms one at a time, these the p-values of these terms come out to be quite a bit different here. So note that almost all of these terms are significant. In the full quadratic model, only C was significant. So the moral of the story is here that the order matters. Now in like a factorial design or a very nice RSM where you have no restrictions on your design space, most methods, will probably give you somewhat similar answers, but here we got completely different answers. So what I would suggest doing then, whatever your optimization is, try to actually optimize using both models and check to make sure that there isn't a huge discrepancy. Now what I'm going to do here is I'm going to maximize both the response using both the forward and the backward model. Turns out in this situation the occurs at the same point in the design space, which to me makes me feel a little bit better. Hopefully the optimal points should occur at similar locations. However, notice that the forward model predicts a response of 127 and the backward model predicts a response of almost 130. So the maximum occurs at the same point in the design space. However, in my opinion, the predicted response using the backward model is probably more accurate here, right? Because it seems like it's the better predictive model. Final suggestion here, actually perform 4 to 5 confirmation runs at this setting here. So go back, perform a couple independent runs at the 0.802 settings, and just double check to make sure that the average of those responses falls in this prediction interval here. Next example. A mixture. So for those of you that know what a mixture is, it's basically a design where the factors have to sum up to a fixed total. In this case, the factors are proportions that sum up to 1. Let's say we have a highly constrained optimal mixture design. A goes from 0 to 11% of the total mixture. B goes from 0 to 11% of the total mixture. C goes from 89 to 90% of the total mixture. And there's also an additional constraint that A plus B have to, in total, be between 10 and 11% of the total mixture. I can experiment anywhere over this simplex here. I am going to just be experimenting my design space as simply this little yellow sliver here. Not a very nice design space. Okay, so why don't we go ahead and actually use forward and backward selection here. And what I'm going to do is I'm going to, so this is a 20-run design. What I'm going to do is I'm actually going to, Design Expert in this case actually suggests the full cubic model. So here are the terms under consideration. What I'm going to do is do a forward selection with AICC. Notice that it just picked this ABC special cubic term and one of these cubic terms here. Then when I correct for hierarchy, I end up getting these terms here. I'm going to write this down, and then I'm going to go back, and I'm going to look at it, see if things make sense here. And then what I'm going to do is I'm going to go back to the cubic model here and do a backward selection with AICC. Now notice that the cubic term that was picked was different in the forward and the backward selection. So once again, I'm going to correct for hierarchy and figure out what's going on here. The question is, so for those of you that have trouble seeing the spreadsheet, here's what I did. I did a forward and a backward selection using AICC. And I considered these terms here, special cubic. So for those of you that are not that familiar with mixture experiments, you don't have to worry too much, just try to get the intuition behind what's going on. But the forward selection picked the following model, and then it added, AB, AC, BC to correct for hierarchy. The backward selection picked this model here, and then I believe AC was added back in, as well as ABC was added back in to correct for hierarchy. So notice that these models are also, this model here and this model here are also quite a bit different. Which model do we pick? Well, once again, what I like to do is I like to first ask the subject matter expert when I'm doing consulting, does one of these make more sense than the other? In the absence of strong subject matter information, what I like to do is compare the models based on lots of statistics. So I'll look at the lack of fit of the two models. The p-value doesn't seem, nothing really to write home about. Both of these models fit adequately. The predicted R-squareds are almost identical here, so I would expect both of these models to predict similarly. And notice that the backward selection once again actually ends up picking the model with the lowest AICC, even though it doesn't look like they're doing that they're all that different. So notice here that the backward selection produces a model that looks to be a little bit better. And if you actually go and look at the optimization here, this is on the the optimization is done on a different. These graphs are done using a different mixture coding here. If you do the optimization here, you'll see that the maximum occurs at the maximum and the minimums occur at very similar locations in the design space. So this is an example where forward and backward they give different models, but they predict similarly. So to finish up, some practical tips and tricks. Question we get asked a lot, forward versus backward selection. My recommendation is why not try both if possible. If both of the directions produce similar models, then you should have a good starting point. Now notice how I said starting point, I didn't say final model. If there are more potential model terms than runs in your data set, so where you have more terms than you have runs, you have to use forward selection because you cannot fit the model, all the terms at once. There is some empirical evidence and kind of a rule of thumb that backward selection does a little bit better in cases where the design space is irregularly shaped or constrained. So mixtures, for example. And if possible, we didn't do this here because this is kind of the all hierarchical subset selection is kind of the easiest of all of these. You could try it if you don't have too many potential model terms. So let's say I go back to this example here. I'll start with my cubic model and I'll do the all hierarchical subsets here. I'll use an alpha of 0.1. Okay, so I ended up getting a model here that was basically a blend of the forward and the backward model because it put in both of these cubic terms here. Okay. And it looks like it gave me a model with an AICC I think that's even lower than the one that I saw previously here, but not by much. So all hierarchical subsets maybe did a little bit better here. But again, to do all our hierarchical subsets in a reasonable amount of time, you need a small experiment, you need a small candidate set of terms. AICC versus BIC versus p-values. Okay, this is another question we get asked a lot. AICC tends to be a little bit more predictive, tends to be a little bit more popular in predictive modeling applications. BIC often selects too few terms. That's why we've limited our focus to AICC. BIC tends to be used more with kind of uncovering the true, trying to get something that's as close to the true model as possible, which may or may not necessarily be the best predictive model. The p-value method requires actually picking a cutoff. And unfortunately, the results may be very sensitive to whatever threshold you use, so whether you use 0.05 or 0.1 or 0.2 or whatever. That's the one nice thing about these model scoring methods like AICC and BIC, is that you don't have to actually pick a threshold. If different methods produce different models, optimize them both, compare them, see if one makes more sense than the other, and see if the results actually differ. Always use subject matter knowledge. So the examples I presented were relatively straightforward to save time, but you should always check to make sure that if one of the models makes more sense than the other. Whenever I work with somebody on a consulting project doing automatic model selection, I always ask the person, do all of the terms in the model make sense? Finally, are there any terms that were excluded but should probably be in the model because your expertise of the process tells you that they should be in the model. So you may have to do some adjustments. You may have to, after automatic selection gives you a model, I like to consider it a starting model. Maybe double check each term, take out terms that you think shouldn't be in there, put terms in that should be in there, check how they predict, and so on. So this is not an easy one-shot process. You may have to do a little bit of work and a little bit of tinkering on your own. And finally, always perform confirmation runs to check model reproducibility, obviously if possible, especially if you have kind of models that predict differently or predict in similar regions of the design space, but maybe the response that they predict is different. Warning about R squared. This is kind of, I think, the final thing I'm going to talk about here before we start wrapping up. I've occasionally seen people do model selection, note the quotes here, using R squared. Now, for those of you that don't know what R squared is, it's a measure of the percent of variability in the data that's explained by the model. Big problem. R squared can only get larger as you keep adding terms to your model because the residual sums of squares can only go down, even if whatever you're putting in is completely unrelated to the response. Larger models will be favored. In fact, if I put in as many terms in the model as I have runs, I will get an R squared of 1. So don't use R squared to compare models of different sizes for model selection purposes. Now, if you absolutely want to use R squared for something, I guess it can be used. You can make an argument that you can use it to compare models of the same size. But if I wanted to use an R squared measure, I would generally use adjusted or predicted R squared, which penalize excessively large models. So it's essentially R squared adjusted for the model size. And just an FYI, we talked about AICC, BIC, and p-values, forward selection, backward selection, all subset selection. There's lots of other methods out there. I'm not going to talk about them. I'll just point out that they exist. There's something called a cross-validation, which you may run into, which is a which leaves data out, see how well the model predicts on that data, and so on. You could also simply use automatic selection by using predicted R squared, although that's generally going to give you something similar to what AICC gives you. There's this Mallow CP, there's an adjusted R squared, and recently in the last 15 years there have been model selection methods which are based off of regularized regression. So if you've ever heard of Lasso or the Danzig selector, this is more just an FYI. If you're interested in them, you can, I would encourage you to look at Wikipedia. So some resources and more information as we start wrapping things up. If you want more help, if you want more information, feel free to check out our website. In the software, you can right-click. We have context-sensitive help. So you can right-click on any of these cells, and you should get a help entry. So if you right-click here in a cell, click help, and you will get a help that pops out. This was all done very well and by Wayne, who put in a lot of time into making this as easy to use as possible. So any of these cells, or most of these cells, should have a help entry. There's also these tooltips here, which we encourage you to use if you don't understand something that's going on in Design Expert. There's a read-only form that you can check out that has some information there. And again, this is the email address I put at on the very first slide here. If you have any questions about anything I said, any concerns, if you'd like more information, more resources, you can email us here and we'll try to get back to you today. And finally, you can also check out our YouTube channel, which has a lot of our webinars, previous webinars posted there. There's also a couple newsletters that you can subscribe to, and also a blog that you can check out, which is maintained by one of our co-founders, Mark Anderson, which is a little bit more fun and lighthearted. So I'd like to thank all of you for joining us. Have a great day, have a great evening. And we'd like to wish you the best of luck in all of your future DOE work. So thanks again, and we'll hopefully see you again in the future. Bye-bye now.